Okay. All right. So we're live on the YouTube now. Let's see. I think.
Have you given me the sharing rights?
Give me a second, please.
Yeah,
Okay. So. All right. So I'll just do like a quick intro and then I'll hand it over to you. Okay.
sure. Yep.
Yeah. All right. So welcome everyone. We have a few people here. That's good to see. A lot of people are interested in these type of like NLP talks, which I'm excited to continue like hosting and doing in the future more as well. More like workshop types. I was mentioning to Pratik that we want to do more like live sessions, things like that. That could help people to get an idea on how to actually build applications around like modern techniques like deep learning or natural language processing. And I think the search use case is a great use case because as I was telling Pratik, we're going to see a large adoption of this. I think as an engineer, NLP engineer, even a machine learning engineer, it's great to have this knowledge and how to quickly build out search solutions not only internally but externally as a product as well as application. And Pratik has a lot of experience in this. He actually did a talk before and introducing like neural search and these ideas and different technologies that are used. And he reached out to me and said he wanted to do a sequel to that, like do something more like, how do you configure it? How do you actually set it up to actually put it out there? So that was the previous talk. He shared a link just now on the chat. You can check that out when you have a chance. But this one is a continuation of that. And in the future, he's promising me that he wants to do something even better because I also wanted to do a talk around how do you deploy it in the cloud as well. How you deploy a search solution once you have other things and the architectures that you want to use. That's something that I'm also wanted to do, but I've been kind of delaying it because I'm really want to do like a real like 3 hours talk or something like that, like a workshop, almost like a tutorial about that. And I'm just trying to compile that information. But today is about Pratik. He's an NLP engineer. He's now working at Jina. It's a really exciting startup that's working on neural search, building out the technology that you need to build out search solutions. So it's really great to have him here, and I will hand it over to him now.
Thanks, Elvis, for organizing this again. And I think we'll do more of this in the future also. And for everyone, this is a sequel to my last talk, as Elvis mentioned. And so I'll be skipping towards some ideas like why we need neural search, although trying to cover it in a few slides. But this talk is more about some new things that I learned after joining Gina, which is an open source, a commercial open source, but we are doing everything for free right now. So there is no commercial part right now, but it's a commercial open source company where we are making this framework, not a library. It's a framework for neural search engines. And we are targeting all kinds of modalities. And I will try to throw light on how to engineer different kind of search engines with Gina. And it makes it very easy to spin up search engines. So let's begin. You guys can see my screen, right?
Yeah, we can see it.
Awesome. So a bit about me. I'm an NLP engineer primarily, not a data scientist. I just work with NLP solutions. I like having random discussions and try to help people with the problems they are facing. I also have this community where we discuss these different kind of problems around data science and try to find solutions. It's called Maxpool. I will link it at the end. And I also argue a lot with people that they should join startups if they are young because you get to learn a lot of things. And I'm very startup pro person. I also write blogs on Medium as well as Substack, which you can find this on the subdomain blog and newsletter. These are also around NLP only. And I have made these small tools, decision trees, I would say, for selecting the models and selecting how to do the deployment. Those are also something I will throw light later. And the last one is my portfolio website. So why neural search? So suppose you want to make a engine where you can write in text, the query is in text, but you are actually looking to search images. So suppose you are searching a kid playing and it would give out results like this. If you are searching for a man with an orange hat, that's kind of weird, but if you want to search something like that, then you need a something called cross-modal search engine which understands this kind of query. And you might think that where is this useful, but let's imagine that we have different kind of photos in our mobile and we want to just search for the photos of our birthday with cake, and we just write uh, photos with cake and it gives us the result. So that would require something like this. There are also different approaches to this kind of search engines, but this is one of them. You can find that example over here, uh, where we have written down all the things that you need to do to make this kind of search engine. This deck will be available openly, so no need to take notes or anything. Just focus on the slides for now. Then let's say you have a different kind of search engine where you take an image, but you want to apply some alteration to it because you're not completely happy with the image. You're searching for some kind of image for maybe writing a blog or maybe for different kind of content. And you want to search a image like this, but with no people and switch to nighttime. So that is two modalities. You do not have either text or image. You have both the modalities going in. And the model has to find an image which satisfies your both the queries. So then it gives out the result like this. The people are gone because we asked for no people, and it's a nighttime, so it's a nighttime. So this is called a multimodal search engine. This was also called a type of neural search engine. Now, again, you will think that what is the application of this? Like this is not sounding very real world use case, but this has a use case in fashion industry, where if you have, let's say, a website like Zalando, some of our founders are from Zalando. So suppose if you want to find, if you have an image of a cloth of a friend, but you want to apply certain alterations to it as per your need, and that you can do with this kind of search engine, that you give an image and you give replace with 3 4 length, so it will understand that it's looking for this kind of design but a shorter one. And you can also have this alteration of the color. You can also do some of these things with filters, right? We are very used to using filters, that you just give an image and let's say you select a color, but this allows you to write your queries in natural language. And there can be more complex use cases where even filters are not enough, like how many filters you would have, literally. So this is also available on this link, which you can check out later. Don't, that will be showing a lot of links. Don't open it right now, otherwise you will be diverted. And now the whole landscape of search is changing, and there are a lot of new use cases, I would say, that are coming up around search engines. It's actually becoming a part of different systems. It's like a first part of a lot of different systems. So it can be used for entity linking, like earlier approaches were like detecting the tokens and then classifying them. But now you can do this kind of stuff also with semantic search engine. There was this recent paper by Facebook. Uh, then you can also do translation. Now that was something we never heard of, but this paper also came out recently, which uses nearest neighbor for machine translation. Nearest neighbor is okay, again a very search engine kind of terminology. Then in question answering also, it is used in a way that it has a retrieval writer framework, that you retrieve a lot of related uh, content from your database. You have a query, and then you have a huge database where answer is lying somewhere. Maybe it's not a direct answer, it requires a reformulation. Then you retrieve using semantic search a lot of relevant documents, let's say top 100 sentences, and then form an answer out of it using some other model. So the first component is actually a semantic search. Then it's also used nowadays in language model training. I have not read this paper, but from the language of it, it sounds that it uses more data at the input by retrieval to train the model even better. And we also have this old paper from 2018, which was again about summarization. It uses BM25 for the retrieval, but ideally we can use this semantic search also, where we again have a summarization problem, and we can actually find the relevant things and summarize it. Now, let's have a real world text search problem, polysemy. Let's say you write just train model, let's say randomly. I'm just taking this scenario. I actually found out this on Twitter. It was trending. And so you write train model. But train model also means this. And for some data scientists, train model also means this. So there are always this kind of nuances that come in different kind of engines that actually require more complex nonlinear function, which are our model. So that's why neural search has an edge over other engines. Of course, it also has problems, but if you have good amount of data, you can train the model to understand this kind of things. And maybe this is not directly decipherable. Maybe if you give image, then it will understand, okay, you give image and text and it understands, okay, it's looking for train models, not a neural network related thing. And maybe we can solve it via passing a context, like past user history of searches, and then it will understand, okay, you are kind of a data scientist who always searches about something related to deep learning neural network, and so it will give this kind of result. So those can be done by neural search engines. There is also a blog by Gina on this, which outlines other use cases where neural search has an edge. I also gave this talk last time. There is this link over here, which you can't see because of this one, but you can also check out the video, which I also posted in the comments for more context. Now, let's discuss about the anatomy of neural search. Like, there are these different kind of search engines as per different modalities. I primarily have talked about text only so far in my previous talk, and but there are different kind of engines where we have to encode other kind of modality like image, video, audio. Like image would be, let's say, Google image search engine. Audio will be like a Shazam, and video can be used for finding recommendations for a similar video. Like you're watching a video and you want to find similar videos of that kind, then you can do that also. And I showed you how multimodal is used and cross model is used. So it's okay to not go neural approach for text. You can just use symbolic search engine like Elasticsearch. Uh, but if you want to make a search engine for image, video, audio, other kinds, then it's very much preferred that you have to go to the neural approach, because the classical way, the statistical way of encoding this modality is okay, not great, but it's okay. Like in audio, we have like MFCC features. For image, you might have some other kind of features from OpenCV kind of library, and you can use that also. But people like to go with the latest neural approaches. So that's why neural search is important, and it's going to be playing more and more part in our life. Given that earlier everything we were writing in text, nowadays we are sharing lots of images and videos. So of course, the search and recommendation will also be based on those in the future. Now, what is the like a general pattern of these things? We cannot keep on writing the framework for different kind of modalities again and again. So we have to abstract out the general pattern from it, so that we can have those modules, and then you plug and play different kind of encoders and indexers, so that you can have a different kind of search engines. So there are primarily two paradigm for making neural search. That first you have this index data, which is, let's say, tons of data, and then you have document. Let's say you are talking about NLP. Then if you have a document, then you might want to break it into paragraphs, sentences, words, phrases. So you can do that as a crafting process. This terminology is relevant to Gina, so that's why I'm using it. Otherwise, you can call it a segmenter also, anything, tokenizer. Once you have broken it down, then you have to encode it via the neural search encoder. So this is the encoding process where you convert this data, which is array, and it passes to a model, and then it comes out as a vector, which is the representation of the whole thing. So that is this process. And then we index the vectors into some kind of indexer. And if you know, there are different kind of indexers also, nearest neighbor kind of, sorry, nearest neighbor, but there are also approximate nearest neighbor. So based on your requirement, you have to choose those kind of things. Also, you just not only index the vector, you also index the original image or text also, because when you are retrieving the result, you do a similarity matching, which I will show, which is this part, that you index the whole thing, and you have this ready-made index, which is now used in the querying process. So the query is coming, then again you have to do the same pre-processing that you are using for this one, which is very similar to our ML pipeline. Then you again encode with the same thing which you are using. Then you do the vector similarity over it, and you get the similar, the relevant documents. And then for those documents, you have to actually get the original, uh, what you say, the original document itself from the index. So it has a two kind of index: it has a vector index and it has a binary index. So you get the similarity with the vector, cosine, or other kind of metric, and then you get the original document. And also sometimes you want to rank it in a different way. Like distance is something that you want least, but cosine similarity is something you want max. So there can be mean ranker, max ranker. Then there can be other kind of rankers, such as you are breaking this document to chunks, but then you do the similarity over the chunks, but then you want to retrieve the original document, right? Like when we write on the Google, it tries to find out that information in all the web pages, but it actually requires the original document to be retrieved. So that requires a different kind of ranker, which maps the chunk to the original document itself. So that is also something integrity. Now, what do we require? Suppose you are just working from scratch. You have no idea what are the frameworks available in the world. As a minimal, not a search related framework, but just basic encoders and indexers you know of, and you have to stitch everything and make your own neural search. So that is something that I used to do. We also had custom use case. You cannot go with a framework all the time. Sometimes you have a custom use case and you have to write something on your own. So what is required when you actually make the search engine from scratch? Uh, just a second. Elvis, should I turn on my video?
If you want to do it, it's up to you.
Okay, I want to do it.
Okay.
I have to stop share it. Okay, this one.
Yeah.
Can you see my video now? My face?
Yeah, we can see it.
Okay. So now let's make a neural search engine from scratch. For that, what we need is a preprocessor that I was talking about, a crafter, segmenter, tokenizer that we need. Then we need to have an encoder, a neural model. Now, of course, these things are easy to say that you just take this and take this one, but you have to actually write this implementation, either functions or classes for it. Then you need a binary indexer for saving the original document. And you also need a vector indexer for saving the vectors. Then you stitch this together and maybe you create APIs for everyone and it's a microservice architecture. Then you write different methods or classes for indexing the documents. And then once it is indexed, then you have to query it for maybe evaluating the model, like how good it is. Or if you are ready, then you can just have a API that you are actually going to use for serving it into production. But before that, you have to containerize it, and then later you can deploy it to cloud, which is again a very big problem statement. So you have to do all of these steps from scratch, and if you're doing it for the first time, it will be a lot of things based on, of course, the use case, but it takes a lot of time. Now that was just the basic. This was just basic. Let's come to the real world, high data intensive applications that we actually say. So what are the functionalities that we require if you want to have a search engine which serves at a huge scale? So first of all, we want to have an evaluation methodology to evaluate the model. So that is again like the third paradigm. I already told you about index and querying, but evaluation is like the third paradigm that you need to have to evaluate different kind of models, because you just can't serve any encoder, right? You would ideally want to try out different encoders and see which is working good for you. So that is what you need. Then uh, you can have large data, and of course you cannot just put it in one small server or even a big server. Sometimes the data is just too huge, like there are so many use cases that the data is in TBs. So for those, you have to break it into chunks and then manage the chunks. Oh, sorry, that was sharding. For chunks, I mean that you have this recursive data structure where you are not dealing exactly on the similarity level with the document, but you are breaking it into smaller and smaller chunks. And that is actually very problematic at the implementation level. Like you might be able to hack a way towards one kind of just one level chunk, but what if it's a two level chunk? What if you want to check the similarity at different levels and just propagate it upwards? So that is working with chunks. Then because you want to have maybe running more than one instances of encoder, because if you're dealing with ML, then you always know that the pre-processing always cheap on the compute, but the other steps like encoding, they can be compute heavy. And so if you want a throughput without a bottleneck, then you need to have uh, parallel processing also. And if you nowadays we have a lot of multi-core servers, so definitely want to have this parallel possibility. Then it's easy and good if you can just configure a code, configure the whole code as some template, as a JSON or YAML or a config parser file, where we just define things and it runs out of the box so that we can quickly iterate through things. We can also have different kind of search engines. Otherwise, it's always easy to write for very specific use case, but in big companies where there are different projects going on, there are different use cases going on, and then if your code is very tightly packed monolithic kind of stuff, then you will not be able to deploy a lot of things very quickly. Then a lot of data requires certain kind of filtering on the key, that uh, you want this kind of price range, or you want this category of thing. So those filtering also needs to be there, which is absent in like the basic search engine. Then you want incremental indexing, like on day zero you have 1000 documents and you indexed it, but on day two, let's say you have 10 more documents. Now what do? Do you index all the 110 documents, or you have some mechanism which checks for the duplication and skips the document which have been indexed earlier and just index the 10 more documents? So that requires a certain kind of engineering also. Then for encoding process specifically, you need to have that mechanism that your code runs on CPU and GPU. You might think that this is easy, but if you're working with different frameworks, PyTorch, TensorFlow, and everyone has their different way of dealing with this, then you need to have those kind of uh, decorators, I would say, because we use decorators, or you need to have something injected everywhere so that it detects something and then automatically takes care of it. Then of course, if you have deployed things and you want to see if you what you deployed is actually working at at the speed, at the latency, or at the throughput that you have, then you need some monitoring dashboard. So that is also a part of the regular ML ops. And you once you make this hack this pipeline, then you also need to test it rigorously. So you also need to have expose the API and then test it rigorously. So you need some kind of Streamlit kind of demo, let's say, for testing it. So all this is like real world use cases. Apart from that, there are also other problems that uh, if you are working with very large data, you want high performance. So you want a high performance API. Like REST would not be great for, let's say, image search, because the data transfer that happens in REST is higher than what happens in a gRPC with protobuf. So you want to have that kind of compression and things so that you can have faster latency APIs. Otherwise you will be wasting a lot of money, because certain use cases require a very fast serving. Then you want high availability. So what I mean by that is that if you have this all these components, a crafter, a encoder, an indexer, all those, let's say you are just have each has only one, and maybe they are distributed. What if one of them fails? Then the whole search engine just fails, right? And there are different ways to deal with this, with with the orchestration framework. But what if the framework actually provides it out of the box? So you need some kind of replicas. So if one falls, then other is definitely there to pick it up. Then, since you have a lot of data, then you of course you wonder whether you should put all the data in the memory or you should have it on the disk. It's good if you can have it on the disk, because disk is the storage is always cheap, and you can still do your stuff. So you need to have different kind of engineering for that. Now we do lot of cosine similarity all the time, like that is the bread and butter of this whole matching thing. So we need that high performance cosine similarity. Now, if you just take the SciPy or NumPy and just write out the method out of the box of doing the cosine similarity function, it's not the optimal way. So there is another way of writing things, that you break it into different components as functions and then do it. So that is some hack that you need to do. Of course, you can do it on your own, but it's this all small things add up to something so much that you will get tired if you are working towards this high performance thing. Then it's always easy to do the cosine similarity and then take the top k out of, then sort it and then take the top k out of it. Uh, but what if we can do better? Like if you want to find just the first uh, if you want to find just the top one, then it's a linear search, right? You do not need to sort it by n log n. So what if you want just a top k? So there are some tricks in the NumPy called arc partition that we actually use to have this high performance top k. And later, if you are doing some GPU serving, or if you want to batch things for some reason, then you need to have this batching functionality into it. Otherwise, even if you deploy in GPU and if there is no batching, then there is no sense. And the requests are always going to come in the batches. So you need something that, sorry, the request is something that are only going to always going to come individual. So you need some batching layer which batches things, and then you can query it better or index it better. That is all the functional requirement. After that, you also have to deploy it to cloud, because everyone is on cloud now. And once you're on the cloud and we have some microservice, then you need to have this way to handle things in a distributed way with this high availability and performance. So you need some orchestration for sure. And then if everything is distributed, then how do you log it? How do you merge the logs? How you see the logs at one place? So that is another problem. So it quickly expands. Like I have been into this phase earlier, and I was able to hack a solution. But every time a problem comes, and I will be like, oh my God, then I have to do this and that. The problems always keep coming. And these are the kind of list of problems that you will face. So you can go this route if you want it, or the good news is that you get all of this for free with Jina. So what is Jina? Jina is a cloud native neural solution that using which we can use the state of the art models out of the box and make and spin out a search solution very quickly. Jina actually sits between, let's say, certain use cases and very low level frameworks. And we are a framework which sort of has a recipe of using this low level libraries, which either you have to hack or we have created it for you. And you just define it easily using Gina and make search solutions very easily. It's also called kind of TensorFlow for search. The reason being that TensorFlow has, and now PyTorch also has this, that it has a core that you use for training. Then it has different model called TensorFlow Hub, where you can get all the models that are available by TensorFlow. And there's TensorFlow serving also, which for extended things. Sorry, TensorFlow extended for different kind of things like serving. So we also have this similar kind of thing. We have a Gina core repo where it's only the core modules, and we have Gina Hub, which where we have different adapters like encoders, indexers, rankers, evaluators, which you just select and then it becomes like a pluggable thing. What can you do with Gina? It can help you make semantic search engines for text, for short and long paragraph, whatever you want. Then it can make help you make video search engines. It can have cross modality. It can have multimodality. It can help you make audio search engines and of course image search engines. So it is having almost all the things that you will be requiring in a real use case. Now, how Gina works on on the low level, what we do is we have this concept of P and pods. So P is like, let's say, an encoder or an indexer, and we put that as this thing is called P, and we put it together in a pod, which is kind of an encapsulation, and this things becomes pod. It's all these things, and you then link it together with the thing called flow, where you define that first use this pod, then use this pod, and then use pods. Then all of this like chain together nicely, and they work for both index as well as query. So this is how the whole thing looks like if you look here, the index is like the fast indexer, and the same index is used for querying. The API is exposed as well as REST as well as gRPC, whatever you want. Then there is a persistence layer for for checking the logs in the dashboard. And there is also this thing called Gina box. So there are two ways to define our three ways actually of defining the flows. Either you define it via Python code, or you can define it via YAMLs, or you can have this UI called Gina box where you just select things and it will create the whole YAML for you. So this is the future vision. You just select things and it will be ready. No need to write Python code or anything, because if you make things Python oriented also, only Python users can do it, right? But if you keep it open, then of course JavaScript people can use it, which is like the most number of developers in the world, and so it becomes kind of language agnostic. Now, what is this amazing thing about the data structure of Gina? That it's recursive in nature. That suppose you have this full text at the root level, the whole document, which you can have break it into paragraphs via some crafter that I was talking earlier. And you can have another crafter which will break it into even sentences and maybe words. So we store all of this information in the document. You can also remove certain information that you are dealing with this level. So you do not save this, you remove this if you want. Of course, you always want the original one, not necessarily. Sometimes you only want the sentences. So you can have this kind of document structure which makes it very very powerful, which I'll show with the use cases. So how this whole full-fledged looks like: at the root you have the full text, then you have the paragraphs, and then you have the sentence and the words. And how we defined it as a traversal path in the YAML. Uh, what you do is that you define that you want something at the chunk level, or chunk, which is a chunk of chunk, or even more chunk level. And this M denotes that whether it's a match for at the root level or it's a match at the chunk level. So you have this language in the Gina through which you can interact with the document by saying I want something from the chunk, or chunk match, or chunk. You have that kind of flexibility, and it does not have any depth limitation. You can just go any depth. Now let's see one example of working with chunks. You can then later explore it via this link. So suppose you have lots of lyrics, and we often hear some words in a song and we want to check out the whole lyrics. And how can you make this whole search engine on your own? So suppose you have this whole lyric, and this is the indexing flow that you have document coming in, and we have this full lyric which is passing to this and also getting stored in this document indexer. We also always want the whole lyrics, right? We just do not return back a matching sentence of a lyric, so we also store the whole document. And then it goes to this, then it breaks this into sentences because we want to match the lyrics at the sentence level, or the phrase, whatever the thing is. Once we have broken it, then encode it so the text became vectors. Then we want to save these vectors so that we can do the similarity later. So we put it into this indexer and then complete the whole flow. The join all is just completing the whole flow. Now, how do you define it in the YAMLs? Now, YAML is like the most easiest way to define this, very user friendly. So the crafter that is breaking is like a sentence-sizer module, which exists in Jina Hub. So these are the adapters I was talking about that you just reference it via this language, and you say that with minimum sentence length of 6. So this is like a parameter in this sentence sizes. So center is actually a class written in Python, and it takes certain arguments, and you can change the value of those arguments or pass if there is no default via this kind of way, that with this value do something. Once you have crafted, you want to encode it. So here we are using the transformer torch encoder. We have a TensorFlow torch encoder. Uh, so we just reference it, and with pooling strategy of auto, pretend model is distillbird, max sentence length is 96. With this kind of configuration, I want to encode it. And what I have to do is that during the search as well as index request, I encode it at the traversal path of C, which is the chunk level. So chunk is like one level less. So we broke the whole into sentences using this. And during the indexing time also, we create the vectors for the chunk and index it. During the query time also, like index request and search request. So during query time also, we take the whole thing and break it into sentences, and then do the similarity at that level. So that's what it's meant. This is just encoding. We do the similarity over here. That we have this compound indexer. So these are pods actually. This is graph pod, encoder pod, this is chunk pod. This is a compound indexer which has two components. It has a numpy indexer for the vectors that I was talking about. It has a binary indexer for the actual lyrics I was talking about, this sentences, the broken down sentences. Then we define, so on the top we define things, and on the bottom, what happens on the request, we define that using this driver, which is specifically for the vector index driver, using the traversal path C, that I want to do something on the chunk level. First, I want to index the index the vectors. And I also want to index the chunk itself using a key value index driver. So the key value is like storing the key values, and there is a hash thing going on for finding to have a ID for the document. So that also happens at the chunk level. During the search request, what I want to do is do the vector similarity at the chunk level. But when I'm retrieving the document, I do not return the chunk, right? I return the chunk match. So this is the language I was talking about, that I'm returning the match of the chunk, and that is taken care by the way the whole flow works. It creates these paths and inside the document, that now I found a chunk of a document, so it will inject those paths and documents inside it. So chunk match is this thing. Once you get it, then you want to actually find the original document of the lyrics, so you use a chunk to doc rank driver. What it does is, the name is quite suggestive of the thing, that it maps the chunk to the original document and then returns the document. So this is how you define the pods in the Jina. Once you have the pods, then you have to define the flow. So it's quite easy. You already talked about it. This is the index flow. First, you have the crafter, which is breaking this, which is the synthesizer. Then you have the encoder. Now here you see that we also have this environment variable Jina parallel. So if you put it one, it will be just one running. It will be running only one in the flow. If you put it two, there will be two. So you get higher availability and throughput also. Then for chunk index, it's storing the vectors, and we can also define the shards over there, that how many shards you want to put, because shards can have a effect on the latency also, like going through one big vector and it's going to be linear search. So if we break it down into small and we have a multi-core processor, and then that can happen maybe faster. So you want to have shards. And if you are having distributed stuff, then of course you want to do some shard for sure. Again, for the document indexer, it's a key value indexer I was talking about. So that everything happens in a flow that you define over here, and then it's completed. For the querying time, uh, you expose the port that you want to work on. Then you have the whatever the query is coming, it is first crafted, encoded. Then you have the chunk, and because you have this lyrics uh, broken into many sentences, you want to merge it again and then return the result. So that is what is this chunk merger, which is a separate thing, small thing, nothing to worry, but that's also a step. And then once you have merged everything and you have these chunks, you actually rank the whole thing, the whole document, chunk to document that I was talking about, and then return the original document from this. So you ranked it and then return the whole document. Now, how does this whole thing look visualization wise? So in Jina, there's this nice functionality that you just define the flow, the pods and the flow, and then you just run these two lines and it will tell you what is actually happening. It's very good for debugging. That you have at the gateway, there is this document. We are discussing the index flow. You take the whole document, save it, but you also pass it to this one. The crafter is there, then there is encoding, and you save the vectors of the chunk and also the documents of the chunk. You complete the whole process. For query, again, the same thing is happening: the crafter, the encoder, chunk, the ranker, and the top. Now, what if this was about text-based thing? What if you want to do something similar but for images? So suppose you have this use case where you will be giving an object at the input and you want to retrieve images from the index which has that object. So that object can be anywhere in the image. It's a part of the image, and we want to find such images and retrieve the whole image, not just the part of the image. There's also another use case where you give the object, the cycle kind of object, and you want to retrieve the objects that were detected while indexing the images. So these were actually detected in the indexed image and cropped and then saved, and then we are retrieving it. So there is a difference. This is about original retrieval and this is about chunk retrieval. So for that, of course, for the object detection, we have to use some model. So we can use this faster RCNN model. It's quite old, but let's say we are using it because it's quite famous. Now, how does that flow look like? This is a bit complex. So if you do not get it, there's nothing to worry. If you go to the repo and just check out everything, you will get it. But this is something that also took me many iterations to understand. So don't need to worry about it. Just try to see what is happening on the higher level. So first, you have this image, and we are doing the indexing with a parallel one. And we take and index the original image. We also pass it to another path where we are reading the image because image is lying in the disk, right? We need to have some method to read it as array. And we detect the object inside the image using the faster RCNN. So here we can use faster RCNN by anyone. Like you can go with the TensorFlow hub also, you can go with the PyTorch also. Then first once you detected the object inside the image, then you have to again normalize it and then again encode it. Over here, the normalization part is taken care by the thing itself. And there's also resizing things happening because you cannot just give any size images, and these images are of any size. So you have you have the first 1 by 255 normalization, you have the resizing thing, and the ImageNet normalization is actually done by the model itself, so we do not do it. Although you can also define it in the normalizer. So you had the original image, you detected the object in it, and then you saved the object itself, the image itself, but you also passed it to normalize it, and then you encoded the image, and you have the vector which you save it. Again, the whole journal is just completing the flow. So that's how the whole index flow looks like. Now the same flow looks like this if you have parallel equal to 2. Just by changing this 1 to 2, you get the flexibility that you will be having two encoder object detectors and encoders working. So this is very nice, right? Like you can get high throughput without doing much code changes. Now the query side is a bit different for this. So the for if you want to retrieve the object, the chunk, then you take the query, you normalize it, you encode it, you vector, and then you have the chunk, and you just return the chunk. You do not do that chunk to doc kind of mapping. You just return the chunk. While in this one, original, you do the same steps, normalize, encode, vector, chunk, and then you have this ranker, chunk to doc rank driver, chunk to doc rank driver. Once you have the doc ID, then you do the original doc in the flow doc idx, which was this one, which we are saying this at this level. This was the chunk which we are referring to in the chunk retrieval, and this is the one which we are referring into the original retrieval. So you get the original doc ID. So this is how it's looking. You pass the cycle, you get the cycle image for the object search. You pass a dog image, you get the images where actually the dog existed. So that is the original search that we are calling it. So this is how easy it is. If you have to implement this all the things by from scratch, it will be a lot of trouble. Now let's discuss a bit on what are the different kind of modules, the adapters I am talking about are available in Jina. So this is again a small mind map I have made for this, which you can access at jinahub.pratik.ai. And let's at the root level, there is this encoders, and there are different kind of encoders. Let's talk about the NLP encoders. So for that, you have this transformer torch encoder. This always work with the models that are supported by the transformers library. So there is this transformer torch encoder. You also have a TF encoder if you like to work with TensorFlow. Universal sentence encoder is quite famous. So we have actually provided that out of the box for you. Then there is this library called Paddle Paddle. So that is quite famous in China. It also has another kind of functionality that is also available. If you want to make a multilingual search engine, then Laser is quite famous and works nice. So that is also directly available. Then there is Flat Text Encoder, which is quite nice and sweet for certain applications. And Farm is getting famous nowadays, and it also has, we also provide that for you. Now in the image, you have again the image torch, image keras, which will also use the models that are available out of the box from the hub. You also have Onyx encoder if you are doing some hi-fi stuff, converting models from one to another format. Then a paddle encoder. Then we also have this custom encoder. If you are working with something custom and you want to fit that into it, we also provide this functionality. And Big Transfer is some latest model released this year, which has nice metrics, but is also big. So if somebody wants to use that, then they can go for this. For audio, we have the MFCC encoder and we have to speech encoder. Both are classical and famous. There will be some latest things. If you find that there is something that is missing, you can write it on your own. It's quite easy. It just requires writing a class and some test cases to check if it is working nicely. And you can uh, write it on your own. If you want to create a pull request for it, we will be happy to add it to our hub. So there are some things which we might not have added, but if you want to use it, feel free to create the PR. For video, we have the torch encoder and paddle encoder. So I think this uses some resonant 3D kind of model. Then for numeric means a general encoder. It's not related to modality. So there is this another library which we can use for VAE encoder. Uh, and this is a layer over that library. If you train some variation and autoencoder via that library, you can use this executor to use it as an encoder, which is useful in certain applications. Then there is, if you are doing some very classical stuff, there is also scikit fast ICE encoder available out of the box. This was all encoders. Then on the crafter side, crafter means breaking things into smaller things. We have a deep segmenter, which is, I think, this kind of state of the art for some sentence segmentation. Then there is PDF extractor, that there is a PDF document, you want to read it. It's quite messy thing, you as if you have worked on it, so that is also available. And we saw the sententizer already, which is some rule-based sententizer. And there's Tika extractor, which works good for certain use cases. It's Java-based actually, but that will also work out of the box for you if you have the dependency installed. For image, we have certain kind of different kind of operation. So we do the cropping, normalizing, reading, resizing, and we used actually the torch object detection segmenter for the object search I was talking about earlier. So that was provided by this one. For audio, we have some audio normalizer. So once we read it, we have to normalize it, and maybe we slice it because we want to break the whole audio into chunks, and then we can encode it and then index it and do and make something like SASM. So if in case you don't know about SASM, SASM is an app that we can use to find similar songs. You just if you're in a party and you like some song, you just open up SASM. It hears for a few seconds, I guess 5 seconds. That audio is enough for it to detect what is the best nearest song for it. It almost always works correctly. I don't know how. Then we want to store the images also, right? We have this key value indexer, which is available inside Jina core itself. But in Jina Hub, we also have these two indexers if you are working with certain use cases which require this. So we have Redis indexer, which is in memory, nice stuff. And we also have a Mongo indexer. Now, this is quite something that people in search have to use. So we provide FAS, we provide Milvus, we provide Annoy. Scan is something latest released by Google 2 months back. We also have ZAR, which is something I've not used, but it's related to distributed index. For now, we have the evaluators. So if you want to evaluate whether this is the best model, whether whole pipeline, not just model, but the whole pipeline was giving the best result for you, then you have to run the evaluation. And for that, we need to use this evaluator. So there is this L1 norm evaluator that you can use, so which is basically comparing the embeddings values directly. Uh, then for ranking, these are the most famous evaluation methodologies. Metrics, the mean reciprocal rank, NDCG, average precision. Uh, for text, there is this edit distance, blue, glue, rogue, which I don't think are very much useful right now, but will be definitely useful in the future. Then we have rankers. This is something that is for very specific requirement that you have you already retrieved the documents, but you want to still re-rank it via BM25 or TF-IDF for certain use case. So that is also available for this. So it's available for re-ranking. It's not original ranking like you would see in uh, Elasticsearch or you see in other things. So if you want to try out this kind of examples with text, audio, image, video, you can go to this link, which is pointing to our examples repo, where we have all the kinds of example, and you can go and maybe check out multimodal. It's very specific kind of use case, but we just implemented it recently. Then if you want to just get started, there is South Park search example, where you index a lot of South Park uh, dialogues, and then you can search the relevant dialogue. So this is, I guess, very relevant use case for a lot of semantics text search application. And this is the whole list that these are the text search, image search examples, audio, video, cross modal, multimodal, and there are some miscellaneous also. We are also working on some uh, distributed stuff. So which those examples are also there, like how you can uh, spawn remotely, like you are on a local, but you are deploying the whole search engine on a cloud, like from one server to other server, you're deploying it. So that examples also we have added recently. So you can check out this and you will come to know a lot of ways of making search engine. So to summarize the whole Jina framework, it's universal. You can use different kind of data, you can use different kind of libraries, and you can work with any kind of operating system with it. It has the whole end-to-end feel to it. From the search engine perspective, you have all the components that you need to make it. It's quite easy to use because you have to write least amount of code. There is a learning curve involved, definitely. You have to understand how to define the things in the YAML, but once you understand it in a week, uh, you can spin out your search engine in the next week. Of course, if you hit any problem, you can always reach out to us for it. Then it's cloud native. We are working on making it very friendly with the cloud. I already talked about remote deployment, but in the future, we'll be integrating with Kubernetes. So the whole thing will be a microservice that encoder is working somewhere else. The crafter is working somewhere else. The benefit of this is that it's not monolithic, so you do not need to take a big server. You have a light server for the crafting. You have a heavy server, maybe a GPU server for the encoder. Then ranking is a light process. So all this can happen on different kind of in a distributed way. So we are trying to make it cloud native, easy to deploy also. Scalability, I already told you. It has this multi-processing and parallel things available, which you can easily do to scale things up for high availability also. And we'll be integrating it maybe with Kubernetes or something else in the future, so that the auto scaling also happens in the cloud. So you do not need to worry about it. You just define your infrastructure and it will auto scale. It's quite extensible. That Gina core is like the core abstract search engine, and Gina Hub is where you put your adapters and you can increase the functionality of Gina for your particular use case. And it of course has a lot of state of the art models available out of the box for you to try. And we'll be adding more encoders and indexers in the future. Some other tools, some decision tree I made that I was talking about, that if you're working in NLP and you want to select model for your use case, then you can go to this chart and see that what is the task you're working with, what is the language you're working with. Suppose you are working with classification, non-English, you're working with a pre-trained model, low latency, high latency. Okay, do this thing. So this is of course not uh, the thing to do. Of course, it's just a guideline, and then you can just get some information out of it. And I would, I've written down some models. I kept it updated till 2 months back. If something happened recently, I'm not sure. And you have a classification, translation, knowledge graph, mobile deployment, NER summarization, what are the best small models available, conversational AI, QA, and semantic search. So if you're working with semantic search, then you can check out this part where you can select the model for the use case. If you see any problem with this, you can reach out to me and I'll be happy to make a change to this. Recently, I also was thinking on what are the different approaches for deployment. So I made this small chart where I would just lay down all the frameworks, because there's so many frameworks you get confused. And I just did a small survey for a few days and put out all the things I could see for deployments. So if you are into deployment, you want to do platform, you want to use platform. If you want to go for open source, then these are the options. If you want to go paid, then these are the things. You want to containerize the things. Okay, you have Kubernetes, Docker. You have something for you have something in AWS also. Data versioning, experiment tracking, and over here I have this logic for if you have PyTorch model. Then you can, if you have any type of architecture, go for torch serve. If you're transformer, maybe turbo transformers. And if you can also convert to Onyx, so you're now into Onyx model, then you can use Onyx runtime, which I think is one of the fastest framework. And you can also again convert it to PyTorch. So it's not a cyclic thing, but if you're starting with Onyx, then if you're into TensorFlow, you convert it to Onyx, and then you can maybe go to PyTorch. So it has this kind of logic where you can select as per your use case. This deck is available on this link, and it will always be available. So if you have missed out on something, want to check it out again, you can go to this link. And I am available to make friends on Twitter. I'm already active on LinkedIn, but I feel I should make more friends on Twitter. So I'm just linking my Twitter handle here. It's NLP Guy. And these are the links, again, the same things I was talking about. And we also have this small community where we are having discussions mostly around NLP, which you can join by going to maxpool.club. And thanks for coming. I'm looking forward to your questions. And yeah, the whole stage is open for questions now.
Thanks a lot, Pratik.
Yeah, my
Um,
pleasure.
yeah, this was great. This was great. I didn't know Gina could do so much already. The last time I checked,
Yep,
it's developing quite fast from what I can see.
true,
And I
true.
think the thing that excites me is the cloud stuff, like you mentioned, having the different
Yep,
components separated. That stuff is quite interesting.
yep.
Anyways, we have a lot of questions, so get
Uh-huh.
ready.
My
I warn
God.
you, there's a lot of questions, really good questions, and I tried to like kind of group them a bit. So
Uh-huh.
you can leave your slides. You can leave your slides because we're gonna go back to the slides in some of them. Um,
Okay.
yeah, just leave them on the screen if you like.
Okay, leave them on the screen. Okay.
Yeah. Yeah. So I'm gonna start with the general questions, and then I'm gonna focus on more production specific questions.
Sure.
Okay, let's see.
Uh-huh.
Okay, so it's a question about video.
Okay.
If you were to search, if you were to create the search solution around video kind of data, someone is asking, I think Soma is asking whether it's possible to extract the timestamp information in the video wherever that that result happened or that search, whatever match, right? The query.
Okay, the timestamp.
Yeah, the
So
timestamp.
you have some incoming image as a query, right?
Mm-hmm.
And you have this image, you have this videos that are indexed, and you want to find that where this particular query related stuff is coming in the videos, which I think is quite relevant to uh, this, what do you say, the TV series industry, maybe, that you are looking for some character and you want to check where is this character coming, or maybe related to something. For that, what you can do is that split the videos into frames. You index all the frames, right? So
Mm-hmm.
the whole video is at the doc level. The frames are at the chunk level. You index all these chunks, and then for the incoming, you check on this chunk level of the frame, and that way the chunk can have this metadata. You have to define the metadata as the timestamp, and then from that you can get this timestamp.
Okay. Okay. Great. All right. So let's keep moving. So there's a question from Money. What is the equivalent of highlighter in Gina search? So I think this is related also to the results and how you can highlight. Um, yeah. So how the
So that,
user? Yeah. Go ahead. Go ahead. I think you get it.
so yeah, good that I know about highlight, because it's a very, very specific thing
Yeah.
of Elasticsearch. And no, we do not have uh, exactly highlight thing, because Elasticsearch is made for full text search, right? While this is made for neural search. So we are more we want to deal more with the vector and things. So we do not have that kind of feature. But what you can hack is you retrieve the chunk also, you retrieve the original document also, and you do check in some way which says that this is the part of the document. These are the words which actually got matched. And if you're dealing with a sentence kind of thing, then the sentence is will mostly be unique in the whole document. So you can highlight that sentence. If you're dealing with a phrase, then that phrase can match in and at multiple places in the document. So that will be a trouble. I hope that answers.
Yeah, I think so. Okay, let's keep moving. Let's see. So there's a question, I think a more general question about ML APIs from your
Mhm.
experience. What would you, what would that API what look like? What tools would you use if you want to build out an API?
That's a tough question actually. It depends on what kind of
Yeah.
complexity and how much time do you want to deal with. Like earlier, I used to spin up APIs in Fast API.
Mm-hmm.
Uh, that used to work, but then I isolated the uh, my API with the model API. Like there are some business information, business related processing that you want to do, like pre-processing and things maybe, and post-processing that I do in the Fast API. But then I have this TensorFlow serving, which I use for serving the model, and then that is like my encoder or my predictor, and that kind of thing I used to do. But of course there are this in the deployment chart that I showed, there are of course different options that are available. And if you want to go further, you can do some grpc custom architecture also. And if you want full scalability, then you can use something like uh, PyZMQ, which we use in Jina for full flexibility of scaling, and it has this push pull and publisher subscriber architecture where the flow of information is happening only one way, like it is coming and then passing out, rather than coming and then returning back. So that is also needed for very, very high performance. So that's why I said in the beginning that it's up to you how much time do you have. If you have never done it, start with Fast API, then do the TensorFlow serving, or it's both are nice and simple, but was abstracting it in the way I told you. And if you want full-fledged complexity, then yeah, go with sockets and ZMQ, publish the server programming, the low level server programming.
Okay, cool. There's some really good suggestions there. So and now moving more to the production side of things. So there was a really interesting question from Nirant. He asking about some data scenario. If
Uh-huh.
if you would do something quite simple like for a small data scenario, using something like Annoy, right?
Huh.
Is 5G something like that? Like that small data is 5G. Would that work? And maybe other considerations that you can talk about in terms of like scaling. How would you scale if you are dealing with a very small data scenario like this? Would Annoy be useful, good enough? And when is it time to scale out to a bigger framework?
So NO is just the indexer, right?
Right.
And
Mm-hmm.
so it's the approximate nearest neighbor indexer that you
Right.
can use. Um, and you can have you can optimize the clusters inside it to have that kind of speed that you want.
Mm-hmm.
In our case, we also have shards,
Right.
right? That is something that either you write customly or we Gina provide it out of the box so that you can have shards. And that is where you get the scalability that you, rather than having a big file, you break it into chunks and then you do your NI over it and then collect the results over that. So you definitely either do sharding on one node, or if you want to do this on multi-node, then that's a bigger problem that you need to think on.
Yeah, can you mention a little bit more about that? Like what kind of issues, things that you want to think about as you scale? So for instance, if you have 100 gigabytes as a scenario of data that you
Right.
want to search on, what would be like strategies, like best practices around that? I think there are a lot of questions around it, so I'm just kind of asking in a general way.
I see. Okay. So I personally have never worked with a lot of data, but
Mm-hmm.
the problem that arises one of the thing is that if you have continuously new data coming in, then you need some auto
Right.
scaling strategy where
Right.
you keep on serving new either keep on having this scaling of the Elasticsearch cluster that requires a particular kind of strategy. You have this uh, data storage strategy that okay is always going to be in shards and it's always going to be added, it's available all the time. and the server side also scaling is quite difficult. And because I have not worked hands-on with this, I have no particular suggestions, but you can have this parallel and sharding mechanism, which is like very standard Elasticsearch terminology,
Hmm.
that you can have many parallels for high availability, and you can have as much shards, I mean optimal shards, of course, not just infinite shards for that.
Hmm.
Is there any specific question that I can take on this?
Yeah. So there was a question like, is there a benchmark on searching text data on, say, a million docs in real time using Gina?
uh, we did some experiment with the Sift database. I don't know if they're available publicly. I will
Okay.
check, and if we can expose it publicly, we will do it. We did
Okay.
some experiments because we are facing some problems,
Right.
so we had to do it.
Yeah, that would be cool. Like, making that public. That would be nice to have.
Yeah.
Then there is I think there's another question. How does Gina compare to Haystack from DeepSet AI for neural search? What are other competitors to Gina? I think you get that a lot. Maybe you can talk about it.
uh, so I have again not worked a lot with Haystack,
Hmm.
but what experimented with it, what I came to know a bit is that uh, it does not have this many components, the adapters I was talking about, and I think it's also NLP specific. I'm not sure. Does it have like other kind of image, audio, and other modules? I'm not sure about it. And Haystack is Java, right? Or is it Python?
I have
Do
no
you know,
idea.
Elvis?
I've never. No,
You
I
have
have
no
no idea.
idea.
I haven't used it, to be honest. Yeah.
I see. I see. I'm not sure, but if it is Java, it's of course a trouble for us.
Hmm.
Uh, but on the important side, it does not have that many components that we have, and not sure if it has this kind of component thing that you can easily add the component to it. Like two things: we have Gina core and we have Gina hub, and if you want to add something, this new encoder that's come up, or some new indexer, then you can easily do it with the Gina hub. I'm not sure if that is also available.
Okay. Cool. So I think there are some questions again from the round asking very tough questions about some upgrades. I think it was more around like breaking API changes. How do you handle them? Like the raise exceptions. Is this done gracefully? Something like that. Um,
Right. So we, of course, keep the old things for now because we have been breaking a lot of things and we are not stable. We are still in
right.
point 0.8. And
Hmm.
something that is still working and it's nice, we are keeping it so that users can keep using it. But we, of course, have decorators for saying it's deprecated. And uh, yeah,
Okay.
that's the main thing we're doing. Yes.
Okay, so I think one last question, and I left this for last because I think this is very open. So in terms of like NLP text search, what would be like the main differences in terms of like performance and relevance of neural search compared to classical BM25? What's your opinion on this?
Okay. Uh, so what happens in text search if let's say the words are very less, suppose it's a one word or two word or three word, then if you do not find that word in your document, it's a total miss, right? But
Mhm.
if you have vector search, then at least you can find something that is similar to it. So it's an
Right.
information problem, information related problem. The more information you have at the query, the more matching you can do. And
Mhm.
of course, there is a token mismatch that is always possible, that still there is a token mismatch. But if you're dealing with very short things, short phrases or words, then vector search makes more sense. The more you're dealing with long sentences, then of course the encoders, the neural encoders also are not good at encoding a lot of information, and they also have trouble. So what we do ideally is we have an hybrid search, which I talked a lot in my last talk,
Mhm.
that we have an Elasticsearch kind of solution for the symbolic search. We get the BM25 score kind of thing. We also have the vector search. the neural search, and whatever scores we get, we kind of merge the scores and then get combine the results and get the final result. So that way, there are a lot of papers which say that this gives us better results.
Okay. Okay, so that's a great, I think, great example that you gave there, and then what will be one of the like the differences and one of the advantages of neural search. But in terms of performance, I'm also very curious about this because I know like the solutions like Elasticsearch using BM25, they have really excellent like solutions to make it, you know, you scale your data, distribute your data, and do this search in a very smart way, and it gives you results quite fast. But with neural search, what changes in terms of like the like framework and what things to consider into performance,
So if we are dealing with very large data, either you have to go with a lot of nodes or shards, or you
right?
can have the approximate nearest neighbor for faster things. So
Hmm.
that is one thing definitely that you need to consider. And one problem that I faced in the past is that the BM25 score is uh, not bounded. It can have any value.
Right,
And the cosine is always bounded. We
right.
always do the cosine, it's 0 to 1. So merging of the score requires some mathematical function, uh,
Hmm.
the intermediate wrapper. So that is also a problem that I faced while making a hybrid solution.
Hmm.
And neural search, of course, one of the biggest problem is that the models are heavy and they take a lot of time. So you need to find out that model which is the smallest and gives you the best performance for your thing. And the first thing that you do is you try out some out of the box model and try to find out the smallest model that works for you. uh, and if that works out enough, great. Otherwise you are in trouble, and maybe you need some your domain's data with the click log, or you have to create your own handmade data set which gives you the good result. So that is also troubling for many companies, that they either do not have the data set, because if there is new company, then they do not have the data set. If there is an old company but they did not have proper logging, then you lost the training data. So that happens a lot because of absence of strategy from the beginning. So encoder is a big problematic thing because it's a black box. You cannot change it easily, and if you have to change it, you have to train it, and training requires some good engineers who would be able to train it. And search log can be very big, so it also requires a different kind of training related engineering and cost also. So those are real problems with neural search.
Cool. All right, those will be the questions. There were more, but I just tried to reduce them, and I think we're way over time now.
Okay.
So thanks very much, Pratik. You did so well on this one. I really liked the presentation and the presentation of Gina as well. And I think you know Gina is really developing fast, as I could see. And I think everyone notes that. So if anyone has any further questions, you can always reach out to Pratik. He shared the links. We're going to share the slides later. I
Yep.
do recommend that you reach out to Pratik. He has a lot of knowledge in this space, and I think we're planning to do another talk about this if you're interested in the future. Myself personally, I'll
Yep.
be also working on a talk. I think I'll do more like Elasticsearch and more text related. But I think the multimodal stuff is really interesting, and it's really cool to see that Gina is really taking on that challenge. So really awesome stuff, Pratik. Thank you very much for spending the time with us today and everyone that joined us today. I think
Yeah,
that'll be
thanks,
it.
Elvis.
Thanks
Yeah,
a lot.
thanks everyone for coming. That makes my day.
Okay, cool. Thanks. Bye, everyone.
Yeah. Bye everyone, have a nice weekend.